Again, thank you for joining us for the webinar today. We're going to go ahead and get started because we know your time is valuable, and we certainly want you to feel like this is a good use of your time. All of us here at Didax Education welcome you. My name is Matt Christensen. I will be your host today. Before we start, I want to point out that you have access through the webinar toolbar to both a question and answer window as well as a chat window. We would encourage you, if you have questions, to use that question and answer window as we go along. Whenever possible, we'll try to answer those questions right away, but we'll also get to any unanswered questions at the end of the webinar. You can also find more information on our website. The webinar is being recorded, and a link to that recording will be sent to everyone within a day or two. Today we're excited to share some information about a new supplemental resource called LEAP, Learning Through an Early Algebra Progression. LEAP is flexible and can be integrated with any instructional resources you might currently be using. Initially, LEAP is available for grades 3 through 5 with 18 to 20 lessons per grade. And in today's presentation, we will learn a little bit more about the research behind LEAP, why this focus on early algebra matters for all students, and how LEAP helps us to meet that need. Our presenter today is Dr. Maria Blanton. Maria is a senior scientist at TERC in Cambridge, Massachusetts, and one of the authors of LEAP. Prior to joining TERC, she was a professor of mathematics education in the STEM education department at the University of Massachusetts, Dartmouth. Her primary research interests include teaching and learning algebra in the elementary grades. Her expertise has led to numerous federally funded research projects and national and international presentations and publications. She's the author of Algebra and the Elementary Classroom, Transforming Thinking, Transforming Practice, and the co-author of the NCTM publication, Developing Essential Understanding of Algebraic Thinking for Teaching Mathematics in Grades 3 through 5. So Maria, we're looking forward to your presentation, and you can go ahead and share your screen whenever you're ready.
Okay, and I think you need to stop sharing so I can do that.
I did that. All right,
okay.
Now we're good.
All right, there we go. Okay, I think we're all set now. Great. Does it look good on your end?
Yeah, you can just maybe launch the presentation. We'll be, There we go, perfect.
Okay, great. Well, thank you so much. We appreciate everyone participating and attending today to talk about something that I certainly get excited about in terms of watching kids' mathematical thinking grow. And this is a work that we've been involved with, my co-authors and I, for a very long time now, over a decade. So look forward to sharing with you a little bit about that, but then I want to save most of the time, hopefully, for any questions you might have. So please feel free to jot those down, and at some point, we'll have opportunity to talk about your questions. I think it's fair to ask, first of all, why should we teach algebraic thinking in elementary grades, something that I'll refer to as early algebra. The curriculum is full, teachers have a very full day, and so it's hard to imagine how could we do more than we're already doing. There are a few things that might be helpful just for some context and background around that question that I think can be very convincing. So let me just share a little bit of that information. Think about these things with me. Believe it or not, this is surprising to me when I first heard this, but a strong preparation through at least Algebra 2 correlates strongly with three things: getting into college, getting out of college, and actually earning in the top quartile of income. So that might be a bit surprising. And in fact, in terms of graduation from college, we know that students who complete Algebra 2 are more than twice as likely to graduate from college compared to students who have less math preparation. So at least that information suggests to us that it's really important that kids do algebra well, that they're successful. And in fact, at least through Algebra 2, that this can have actually important implications for what they do in college and even their life choices beyond college. But you certainly might be thinking that this is really about high school, and I'm involved with elementary grades, and this really does not impact my life. So one more thing that I want to share that I also find very compelling is the relationship between children's early math knowledge and their future math achievement is roughly twice as strong as the relationship between early and later reading achievement. So even if you're in a district where maybe kids perform roughly the same in terms of reading and math and elementary grades, whatever disparities or struggles kids have in mathematics in these early grades is going to be much more greatly exacerbated once they get into high school. So these suggest to me that we need to not only think about how to prepare kids well for algebra while they're in high school, but we have to think about that process before they even get there. So with that in mind, I want you to think about a couple of other points that I think are really a part of why we want to do early algebra. First of all, if you look traditionally at how arithmetic and algebra have been taught in school mathematics, we've used what's been called an arithmetic then algebra approach, where the thinking has been, if we really spend a lot of time getting arithmetic right, if you will, in the elementary grades, the first 8 years in arithmetic, then when they get into 7th, 8th grade, 9th grade, they can do pre-algebra, then algebra 1, and they'll be ready. What we found is actually kids are not well prepared for algebra if they go through that kind of model. And so that's something that's a reality, and it's led to what's been referred to as the gatekeeper of algebra in school mathematics. It's marginalized many students across the board. The other thing to keep in mind is that knowledge demands have changed greatly over the last several decades. So if you look back, it's very interesting to look back 100 years ago, even 50 years ago, at what kinds of mathematics knowledge were important in school mathematics. It's changed tremendously. And just to give you a word picture to go along with that, nobody would want to drive the kind of car their grandfather drove. And that's true in learning as well. So we sort of have these different components at play here, are sort of in contradiction with each other. We've got the fact that algebra, or algebra 2 even, that specifically, is important in high school. Early preparation beginning in elementary grades is important. Yet when we look historically at how we've done this, we haven't done it well, in that we focus too much on arithmetic, then algebra, as opposed to integrating these subject areas. That sort of juxtaposed with how knowledge has changed really has set the stage for what many have described as sort of a train wreck in high school algebra performance. So you get a lot of students who hate math, they don't want to do math, and they choose careers based on not doing mathematics. Yet we are in an age that's increasingly STEM oriented, and so that's not okay. We've got to rethink that process so that we have kids who are successful in math and who have choices beyond what they might otherwise have without that success in math. So that's sort of the context for where early algebra is coming from. And the response to that challenge has been this push to try to build elementary children's understanding of early algebraic concepts in ways that will prepare them for success in formal algebra later. So we don't want kids to go into middle grades, into high school, not ready for this. But there are a lot of questions. What does that mean? What does it look like? What should I be doing, every day in my classroom? So I want to take a little bit of time to talk about what that might resemble, how we approach it, and what we've learned from this particular approach. So let me start with a really simple question. What is early algebra? You may have experience with it already. I don't know your backgrounds, of course, so if you do, just bear with me, because I think it's important to think back through this. Let me start by saying what it's not. It's not algebra early. So when we or other researchers talk about early algebra, we are not talking about taking things that we might think of as typical in an Algebra 1 class and then just doing them in 3rd grade or 4th grade. It's very different than that. There are components that are similar, and certainly even in LEAP, we definitely have kids solve equations, but the motivation is very different and the purpose behind it is different. So our approach to early algebra is based on a framework that involves 2 key components: 4 key algebraic thinking practices and content areas where these practices can occur. And so I'm going to talk a little bit about what they are, but what I'll say now is the entire LEAP curriculum is organized around these practices and this content. So when we started this work, we didn't just sort of sit around and say, okay, I like this part of algebra, I like this task, let's put this together and see if it sticks, sort of some random approach. And I would caution you to look at what you're doing in your schools, what the curriculum you're using is. What is their theory, their philosophy behind algebra and algebraic thinking? There should be some underlying framework that guides how tasks are designed, how lessons are put together, and so forth. And so we've spent a lot of time thinking about what does it mean to think algebraically, what these practices look like, and how do we build them in children's thinking. By the practices, I mean 4 particular areas: generalizing, representing, justifying, and reasoning with mathematical structure and relationships. So let me just say a little bit about each of these very briefly. Generalizing, in that we want kids to notice what's happening in general. We don't want them to be focused, as they are often in arithmetic, just on particular things. So for example, we want them to think about, why is it that the sum of 2 odd numbers is always even? We're not so much concerned with the fact that they just add odd numbers, but we want them to notice these general relationships that happen in operations on number. We want them to be able to represent their ideas. They might represent, for example, a functional relationship through words. They might use variable notation in the form of a rule. They might use graphs or tables. There are a variety of ways they can represent these ideas. We want them to justify the generalizations that they make. So it's not, for example, enough just to say, well, I think that every time I add 2 odd numbers, I'm going to get an even number. It's not just enough to make that claim, but think about, why is that true? And not only why is that true, but why are some arguments better than others? And so that's a really important part of how we want kids to think about these ideas. And finally, we want them to reason with the ideas they find, the generalizations they make. And this happens in a variety of ways. So it might be that a child who understands that the sum of 2 odds is always even might then think about, what happens if I add 3 odd numbers? And they might use this earlier claim to build an argument. But more importantly, we want them to be able to take their computational work and use the properties of arithmetic that they see, observe, and talk about. We want them to think about how these properties can make their computational work more efficient. A lot of times kids can compute well, but often it's sort of left to right computational work that might not have a lot of deep thinking behind it. Why is it they compute in a certain way? And what are the more efficient ways that they can compute? And understanding algebra actually helps them think about this type of arithmetic work. So that to us is important as well. The next piece of that framework is where those practices can occur. So the good news is that these practices, or sorry, these areas, or the content areas where the practices occur, are already present really across elementary grades mathematics. So they're not a surprise, if you will, for teachers. It might be in properties of operations, such as commutative property of addition. It might be with relationships about classes of numbers. It might be through a study of the equal sign. It could be about relationships between quantities or expressions through equations and inequalities. It might be about covariant relationships, such as functions. And so what we try to do with LEAP is we took the framework of algebraic thinking practices, and from that we asked ourselves, where are the places where we can get kids to engage in these kinds of practices? And the LEAP curriculum is designed around that. So you see a lot of work with properties, you see a lot of work with the equal sign, you see a lot of work with functions, but it's all about building these ideas and engaging them around algebraic thinking practices, not engaging in things that we might see in Algebra 1 per se. I want to say a little bit more about the LEAP curriculum in terms of the broad picture, as well as some specifics about it, and then I want to share with you some results of whether or not LEAP works. Just in terms of its design, it's over a decade of work on our part with about $9 million of federally funded research. So it's been something that we've spent a lot of time and thought in testing and developing. So it's not something, like I said earlier, that we sort of threw together to sort of see what would stick. Matt mentioned that each grade level has about 18 one-hour lessons. In grades 3 through 5, there are one-hour lessons, but in the earlier grades, which we're designing now, they're more like 30 to 40-minute lessons. So again, the idea is to have a K through 5 approach to early algebraic thinking when this is all done. As I've said, we use these 4 practices, and the point there is to build something that's connected and coherent across elementary grades. So, for example, if we're developing kids' idea of their notions about variable notation, we start with kindergarten and we go through grade 5, and we have very specific ways we want kids to understand and make sense of variable, not just use letters blindly and rotely, which has been the problem for years now in terms of kids' understanding of algebra, but we want them to do it intentionally and with meaning. The curriculum is designed to be accessible to all learners. So when we're designing and testing our materials, we go into all schools, all demographics, wherever. We even choose schools that might be specifically focused around kids who struggle with mathematics or things like that, because this is really not for the top 10%. It's really for every single learner in the classroom. It's based on a lot of extensive research, our own as well as others. And we've shown that it does actually transform students' thinking, and it builds their algebra readiness for middle school. And I want to give you a little bit of data on that in just a second. But let me first talk about what I see as critical design features of the curriculum. All the lessons are built around small group investigative activities that engage students in higher order thinking. The lessons are designed to promote not just mathematical discussion, but also writing about mathematical ideas. Research shows that students who not only talk about their thinking, but also write about it significantly outperform those students who simply talk about their ideas. So it's great that they talk about ideas, but we want them to write about it as well. Every lesson involves teacher-focused questioning, and there are two reasons for that. For one, teachers don't always have the background for teaching early algebra, so we build questions into the lessons to scaffold their thinking, to support their work, so that they don't miss out on the important questions in a lesson. But those questions are also designed to build meaning for mathematical ideas. So again, if we're talking about variable notation, we have specific questions that we want to ask students to make sure they're building the right meaning for those ideas and are not just using them remote in a way that doesn't have meaning or is remote in some sense. We also include, especially in the lower grades, particular concrete and visual tools that we know will support learning through our own research. We've looked at this, and these are tools that kids can integrate in their activities so that it helps them understand the concepts at play. Each lesson has ongoing formative assessment points that can help teachers monitor progress. And finally, the lessons overall use a spiraled approach that develops understanding across grades. So what we don't want to do is, have a curriculum where in grade 4, lesson 3, they learn a concept and they never see it again. But across grades K through 5, we have a set of core algebraic concepts, practices that we develop continually, so that over the years, you get this sort of widening circle of complexity that kids are increasingly engaged in and become more successful at. Does it work? That's sort of the litmus test for any of this. Does it actually work? So I want to share with you the results of a randomized study that we recently conducted in 46 schools, about 3,000 students participating, and LEAP in grades 3 through 5 was taught by classroom teachers. So in that study, what we found is that at pre-test baseline, grade 3, everybody was the same. LEAP students and control students were statistically the same, although actually control students actually performed a little bit better than treatment students. But by the end of 3rd grade, LEAP kids had significantly outperformed control kids. And they maintained that advantage across grades 4 and 5, so that once they left 5th grade and were entering middle school, they were significantly ahead of control kids in their ability to engage in what we view as core algebraic thinking concepts and practices based on a written assessment they were given year by year. So these results were quite strong for an intervention of this type, to get that type of gain and to maintain that over time. But it certainly left us with the question of, what about those kids who maybe were struggling? What can we say about them? Did they get left behind or what? So when we looked at 9 schools participating in this study, 9 of the schools were considered 100% low SES. They were, in terms of demographics, 90%, at least 90% persons of color. So in that sense, there were at-risk populations that we were dealing with. And what we found is that these students too, in the LEAP intervention, actually did the same thing in parallel as the overall sample. So while they started at a lower place and ended at a lower place, still they were significantly ahead of their peers in similar control schools at the end of 3rd grade, 4th grade, and 5th grade. So when they went into 6th grade, they were statistically ahead of their peers in control schools. What's also interesting is if you look at where, in this particular case, where students in LEAP, in low-performing schools, where they ended up at the end of 5th grade, if you compare that in the overall sample to control kids, the LEAP kids in this scenario actually outperform control kids. So they really just amazed us, and that was an exciting finding for us because we really saw the power of this curriculum to support all learners and to help everybody. So they are in fact going into 6th grade at the same level, if you will, as the overall sample, and that was a huge finding for us. So just to put those results in perspective, because obviously we didn't get 100%, and that's from a research perspective, the findings were great, but classroom teachers want all their kids to do at least 100%. Think about it this way, though. When we look at the grades 3 through 5 intervention we did across 3 years, that was about 24 hours each year. And that's a generous measure. 18 lessons, about an hour a lesson, let's just say 24 hours per year. In all, about 3 days of their life in elementary grades gave them that kind of statistically significant bump going into middle grades. And that's just only after the upper elementary grades. So when we put our K through 5 work together, we expect and hope even better results than that. I want to close with one thing, and then I'll ask for your questions. What about standards? I mean, we certainly appreciate, especially if you're in a state that's using Common Core, but if not, you've got your own standards, and they can be sort of a taskmaster where every day you're expected to do certain things. I want to talk a bit about the standards for mathematical practice, and I'm going to put these up, and obviously you're not expected to be able to read these that quickly. I want to show you something about them, though. When we were doing our randomized study, after a year of working with teachers in a particular grade level, we asked them to just take some time and put them in groups, and we gave them a practice, and we said, think about LEAP. What have you been doing with this practice in LEAP? Is there any evidence? So after some period of time, we came together, we talked about it. They also highlighted these particular practices where they felt LEAP was addressing the mathematical practices. And so what I want to show you next is what they highlighted, because I think it's pretty astounding and it tells a really important story. Everything in orange is where they felt like there was synergy between LEAP and the standards for mathematical practice. And if you look at those practices and what it means to think mathematically, they are deeply connected to what it means to think algebraically. And so what we find is that the LEAP curriculum is constantly addressing these practices. It might address multiple practices in one lesson, but there's a rich synergy between them that we feel like builds mathematical thinking among students. So just in closing, what I'd say about LEAP is it's designed intentionally to be coherent in that it uses an overarching framework for algebraic thinking to guide our curriculum design. It wasn't random. It's designed to be connected. All the lessons reflect a curricular progression of increasingly complex ideas across grades. It's designed to be accessible. We've thought hard about how do we incorporate design principles that support struggling learners. And it's designed to be transformative. We know from our randomized study that it does increase children's algebra readiness for middle grade. So that for us is an exciting story. That story is not finished in terms of its writing, but that's where we are now. So at this point, I'd be happy to take any questions you have.
Sorry, we have a couple questions, Maria. One from Glenn. He asked, he says, I'm interested in the relationship between writing about math and math success. Can you describe the structures in LEAP for math writing? That's the first part of his question.
Great. And so when we're writing about mathematics in LEAP, we're often asking students to describe a relationship they see or describe an argument that they think supports a particular claim they've made. Things of that nature. Or it could be something as simple, describe in writing what the quantity is you've represented with a letter. So we don't just use letters, we have to talk about and write about what they mean. Having said that, we also treat this as a place where teachers need to choose the right level of writing because you can't write about every single thing that you talk about. So there is some flexibility in that. I will say this anecdotally, when we were doing our randomized study, we had gone through grade 3 with these students and we were in grade 4. And one of the teachers who was in a school that was not a high performing school said to us in conversation as part of professional development, she said, I've never had students come into my class who were so able to talk about and write about their thinking. So while that's not a randomized study, an inferential claim we can make, we do feel like that LEAP is designed so that kids do have that opportunity to write and talk.
Great, thank you. And then his follow-up question was about where you can find good journal articles to share with teachers that support that. Maybe that's something we can share later. If you have,
absolutely.
I bet you do. So, all right, there's a question, actually a few questions about how do schools, or how can I in my school integrate this with my current curriculum?
That's a great question. And when we did the randomized study, of course, the schools participating all had their regular curriculum in place. What we normally do is we have LEAP designed so that, again, about 18, 20 lessons per year. You can start in September and go about one per week, not every week, because there are more weeks than that in the year. And you can teach a LEAP lesson, and that's one way to do it. And you'll find places where it connects with your regular curriculum. However, after we've gone through that process with teachers, what we find is that they might rearrange some things in the curriculum so that it more closely aligns. So, for example, you might be doing work with functions in grades 4 and 5 that falls in April, but yet we're going to do it in LEAP in March. And so you might change that around somewhat. So there are ways that you can move it. The order in which we do LEAP lessons is not necessarily rigid. There's a purpose in how we've sequenced things, but it can be aligned with your curriculum. One thing to keep in mind, though, is, and this is a place where teachers might think a little rigidly about what they should do, for example, in 3rd grade. So if you think in 3rd grade that you have to do all the concepts that are in, let's say, Common Core, all the standards, the challenge with that is a problem like the equal sign is known to be problematic for students into high school. Yet that's a 1st grade standard. So what we emphasize with teachers is that you can't really think about the standards explicitly within a grade level, but you have to think about the concept being taught and how it lines up with where they're headed. So if we know kids are headed into algebra, they need to understand the equal sign. And that's a concept we actually address continually K through 5, not just in 1st grade. So when you look at our lessons, we've identified particular standards, content standards that they address. It can be, you can have a lesson that has a standard from 1st grade and 6th grade. So it doesn't line up per se with a particular grade, but it's really what's the concept and where is it headed and how do we build that idea.
Great. Thank you, Maria. Okay, we have another question about if you can give an example maybe of what a lesson looks like or what kind of tasks students might complete as they're using the program.
And that'll vary quite a bit depending on what area it's coming from. So for example, if you're doing something in what we describe as generalized arithmetic, then you might have students investigating the distributive property of multiplication over addition. And that wouldn't happen until about 4th grade. But we spend a lot of time thinking about area models, what the property means. We want kids to notice that property in computational work. We want them to be able to make a generalization about what that property looks like, to describe it in words, to describe it in variables, justify why it works using, again, area model. So if we're dealing with properties, we generally take those properties and begin that work in computation, which is an easy place for students to begin, so they know how to do that. And then it's about stepping back and talking about what do you notice? And the noticing then leads into descriptions in their own words about what they notice. And that then goes into a variable notation, so an equation that represents what they notice, and talking about variable, what does that mean, and things like that. Then why does it work? So there are things that kids can do visually or with concrete tools that show why the commutative property makes sense. And we want them to think about it at that level as well. So we're not just interested in whether or not kids can recite a property, whether they can write it down, but we want them to understand why it works. And then finally, we want them to be able to take that property and recognize where they're using it in their computational work. And that is actually something they do quite intuitively well, but they don't always know how to talk about it. So one of our lessons, for example, is using what I know about operations, where we really get kids to think about computational work and how am I using these properties that we learn, but yet don't really do much with them. Other areas might be something like with functions. So functions are always grounded in some type of context, real world if you want to describe it. And from that, students generate data, they organize it, they look for relationships, they talk about these relationships. We gradually move them towards looking at functional relationships rather than simpler recursive types of thinking. And then from that, we want them to represent it using tables, graphs, rules. But ultimately, what we want them to do, and this doesn't happen until about 4th or 5th grade, we want them to think about answering problems that are relevant. So which dill is better, for example, or which diet should this guinea pig be on if he's going to, certain things are important. They want him to gain weight quickly or not. So that kind of work needs time to develop. You can't really do that so well in 2nd grade, but over years, by the time kids get to 4th and 5th grade, these lessons are designed so that now they're ready. They've got these tools. They can think about bigger questions. They can look at their graph. They can talk about their table. They can go back and forth. They can answer questions that are relevant to the context. So I'm not sure if that helped you or not, but anyway.
I think that was a great description. So there's been a few questions to Maria about, one of them I really like because it's broad, and I think we can narrow it down just a little bit. But the question is, how would I prepare my teachers to implement LEAP? And maybe that's a little bit about both materials and training, what that looks like.
Sure, that's a great question. We generally recommend at least 1, preferably 2 days in the summer, sort of a summer workshop kickoff, but with that, follow up throughout the year. So I think it's really important for teachers not to just sort of be left at the start of the school year with no interaction. So that might look different, and it might take different forms. You could do a summer workshop, but then that's sort of combined with either a face-to-face meetings or webinars, things like that help teachers work through their questions and things that they're having difficulty with, things they might not have expected. But I will say this as well, the lessons themselves are also designed to address some of these issues. So they're not just math lessons. There's a lot of time and attention given to how do students think about this context or this particular task? How or why do we design a task in a certain way? What is our purpose in doing this? How might you as a teacher support students in learning about these things? What are ways you can support struggling learners? So there is a lot built into the lessons themselves that are really trying to help teachers work through content, frankly, that they're not used to teaching, that they're now being asked to teach. And in fairness to them, they've got a lot on their plate already. So we've tried to think through that at the level of what the curriculum looks like. But beyond that, it really does, we really recommend some training to go with it.
Okay. And then from a material standpoint, what would teachers need as they implement them?
If you mean like tools in the classroom, for grades 3 through 5, you actually don't need very much. Okay. There are certain, like you might need balance scales and so forth, but you are getting more into the abstract visual world at that point. K through 2 is a little bit different. That has a lot more, it's more tool-based, I guess you'd say, than 3 through 5.
Okay. And then, of course, they would also need the actual lessons, the book with the lessons as well. Great. Okay, so let's see. We have a question about some of these overlapped. So, professional development. We had a question about when K2 will be available.
So we are designing that now, and my guess is those books will be available within the next year. And that's really more of a question for Didax than for us. We have finished pretty much our main testing of those materials. This coming year, we're going to do a short study across K through 2 to do sort of a teacher efficacy study to see how they work with these materials and what changes we need to make a result of that. So there's that level of testing. And then after that, we'll continue to do the kinds of studies we normally do. So we'll start, for example, with a quasi-experimental study, then we'll go into a randomized study. But the materials themselves will be ready before that. That's my understanding. And again, Matt, that's more of a Didax question.
No, that was a good answer to a Didax question. And then I had a question about what motivated you to do the research into early algebra.
Oh, I love that question. Well, I've always loved algebra. And so when I started as a professor at University of Massachusetts, Dartmouth, the colleague that I went to work with there was probably a leader internationally in this field and really rethinking algebra and how we do it in school mathematics, Jim Caput. So it was a natural fit. I worked with him on this, and I've always enjoyed it. So it's just, it's funny. I started out planning to teach high school math. And over the years, then I moved into middle school, and finally now I'm in elementary grades, and that's really the age that I love. I enjoy talking with kids, and anybody on our team would tell you we have found just amazing things with what kids are able to do as early as 5 and 6 years old that just astound us. And it just points to us, emphasizes to us, we've missed many opportunities if we wait until 6th grade, 7th grade, 8th grade. Because when they're in these young stages, these young ages are so open to ideas and things like variable. I mean, if you wait until middle school, then kids have all kinds of problems with variable. But if you talk with a 5-year-old about a variable, they just grasp it so readily. So the work itself is so fun. It's really, and to the extent that it actually will make a difference in people's lives, then it's rewarding as well.
Thank you. 2 more questions. One of them, would you suggest that I start using LEAP with just my 3rd grade students?
Yes. If you were going to just go in and start, I would do 3rd grade and then following in the 4th and 5th. So that's the way it's sort of designed now. You could start with 5th grade, but depending on your school, if you felt like your school was very strong mathematically, you might start with the 5th grade curriculum, but you might decide to start with the 4th grade or even the 3rd grade, depending on where they were. So, but the 3rd grade book right now is the starting point, depending on what, but you could decide what grade you wanted to implement it at.
So it's really kind of an individual thing, depending on your situation.
Right.
Okay. And then finally, I think this is the last one. Will there be resources for parents as well to support the home practice of LEAP?
That reminds me of our first project. We actually started by doing sort of a LEAP homework where the goal was to actually get kids to go home and teach their parents what this was about. We had to sideline that, unfortunately. So we don't have that right now, but that is a wonderful idea. And, maybe we'll put that into the bin of the research projects we want to start working on and do something like that. I think that's a fabulous idea.
Great. Thank you. I don't see any other questions at this point. Maria, if you could just advance to the last slide there.
Oh, sure. Absolutely.
Oh, that's not a problem. So Maria, we really thank you for your time and for this great presentation introducing us to LEAP. You can find out more about LEAP at didax.com/LEAP on the website. We have some sample lessons there. We have information about Maria and the other authors. We have really an opportunity for you to see what these lessons are about and what this program is about. If you have questions that we didn't address today or other things that you would like to talk to us about and how you could implement this, please feel free to reach out to either Ann McManus, who covers the Eastern US, or myself, Matt Christensen. I have the Western US. And either one of us would be happy to talk to you more about this. There's also a general email that's leap@didax.com that you could contact for more information as well. So again, Maria, we really appreciate your time today and all the work that you and your colleagues have put into this program. It's really fantastic, and we're looking forward to seeing how this impacts students.
Thank you so much. My pleasure.